CWI Prep Course, Weld Inspection and Certification, Module 10, Part 7. Learning objectives. In this module, we're going to touch base on magnetic induction fields, magnetic particle testing, equipment and materials, basic procedures and techniques, magnetic particle powders, magnetic particle inspection of welds, magnetic particle advantages and disadvantages.
Magnetic particle, MT. Magnetic particle testing is used to detect surface and near-surface flaws in ferromagnetic, magnetizable materials. The indications provided by this type of test occur at the surface of the part directly above the location of the flaws, and the general size, shape, and orientation of the flaws can usually be directly inferred. Magnetic particle testing is used in receiving inspections and in processing or final inspections, as well as in service inspections. Magnetic particle testing can be used for forgings and castings, for crankshafts and simple plates, for large and small parts, and is extensively used for welding inspections. It is one of the best established non-destructive testing methods used on ferromagnetic materials. There you have MT. Good for ferromagnetic materials, but is a really great non-destructive testing method. It's like one of the best established for ferromagnetic materials. Not going to work on aluminum, not going to work on titanium, but ferromagnetic materials, good system, good testing method. Magnetic particle testing requires the induction of a magnetic field into the part to be tested. If the part has discontinuities in its magnetic permeability, singularities in the magnetic field can exist. These field singularities, or leakage fields, can attract and hold small ferromagnetic particles. Therefore, when a magnetic field is established in a part and small ferromagnetic particles are applied over the surface, some of these particles will collect at a leakage field location, thereby forming indications that can be associated with underlying discontinuities. The basic principles associated with magnetic particle testing involve magnetic properties of materials, magnetic fields, and the visual detection of small particles. Here's a magnetic induction field. The magnetic fields used in magnetic particle testing are usually created by the flow of current, but permanent magnets can also be used. Figure 4.2.1 shows a simple bar magnet with its magnetic field indicated by magnetic flux lines or lines of force with direction arrows. All magnets have a north and a south pole. All magnetic flux lines are continuous and form closed loops. The strength of the magnetic field at any point can be measured in terms of the number of lines of force per unit area, the area being at right angles to the lines of force at the point being measured. The direction of any of the flux lines shown by the arrows indicates the direction that an infinitely small north monopole, which exists only theoretically, would move if it were placed at that point in the field. So you can see the flow of magnetism around this bar magnet. It's like when we were kids, you'd put a magnet underneath a piece of paper and put some iron filings on it, and you'd see the magnetic field. You'd see the magnetic lines of force and how they were stronger at the poles than they were out at the equator, I guess, of the magnet. But this gives you an idea, in case you didn't already know, what a magnetic field looks like on a bar magnet. When an electric current flows in a straight line from one contact point to the other, magnetic lines of force are in a circular direction. In order for a defect to show up as a disturbance in the pattern of the iron particles, the direction of the magnetic field must be close to a right angle to the major axis of the defect. Since the orientation of the defect is unknown, a minimum of 2 current directions must be used during the test. In this figure, circular magnetism is induced in the test piece so that the piece may be inspected for lengthwise cracks. Longitudinal magnetism is induced so the piece may be inspected for transverse cracks. In general, magnetic particle inspection is satisfactory for detecting surface cracks and subsurface cracks that are not more than 1/4 of an inch below the surface. In this sketch, you can see there's a couple of different options for inducing a circular magnetic field into a part. In the head shot in A on the left, you're running a current through the part, and it's inducing a magnetic field. And then on the central conductor on B, you're just running a current through a conductor that's going through the part, and then you're inducing a field in that way. And then you would sprinkle your iron powder or your iron filings on there and look for your defects that would show up depending on what your sensitivity is. Usually with magnetic particle, setups for more than one direction must be made to ensure that all discontinuities will be seen. In some cases, the current may flow through the part. In other cases, separate conductors or coils will be used, just depending on what you've got going on. To locate a defect in a part, it is essential that the magnetic lines of force pass approximately perpendicular to the defect. It is therefore necessary to induce magnetic flux in more than one direction, since the defects are likely to exist at any angle to the major axis of the part. This requires 2 separate magnetizing operations referred to as circular magnetization and longitudinal magnetization. The effect of the flux direction is illustrated in Figure 8.15. Circular magnetization. Here you can see they're doing circular magnetization of a camshaft and longitudinal magnetization of a camshaft. In the circular magnetization of the camshaft, they're just running an electric current through the camshaft. In the longitudinal magnetization of this crankshaft, they're running, they've got a huge magnet on the outside of it, so that's how they're inducing the longitudinal magnetic field into this part. Here's a couple other options for inducing a magnetic field into a part. You can use a yoke to induce magnetization, or you can use a prod setup to induce magnetization. Usually setups for more than one direction must be made to ensure that all weld discontinuities will be seen. It should be noted that in some cases the current may flow through the part, and in other cases through separate conductors or coils. Magnetization by injecting current into the test item is usually preferred whenever maximum sensitivity to tiny flaws is desired, or whenever a magnetic field cannot be conveniently induced in the test item by other methods. However, if the part under inspection is magnetized by injecting current into its surface, care must be taken to avoid arcing, as this may severely damage the surface, particularly whenever handheld prods are used to inject current. Arcing tends to occur whenever the current contacts are dirty or are moved during excitation. A simple way around the arcing problem is to securely clamp the contacts to a clean area. When magnetization is induced by placing the part in an external magnetic field, the arcing problem does not occur. Magnetic particle testing. Steps in an MT procedure. Component pre-cleaning, introduction of magnetic field, application of magnetic media. This is the iron powder with a color, a paint attached to it, and then interpretation of the magnetic particle indications. MT can detect both surface and very near subsurface defects, cannot inspect non-ferrous materials such as aluminum, magnesium, or most stainless steels. Really powerful tool when you're working with iron and steel alloys, but not so good with aluminum, magnesium, and most stainless steels. That would be like the 300 series austenitic stainless steels. This is not going to work. Titanium doesn't work. The equipment and materials required to perform magnetic particle test can be as simple as a strong permanent magnet and a supply of magnetic particle powders. However, sources of electrical currents with control over the current magnitudes and directions, magnetic coils and yokes, and tanks for holding magnetic powders either in dry or wet form can all be considered as necessary facilities for most magnetic particle testing. Here's a magnetic particle testing station in a cabinet form circa 1985, but you'll still run into a lot of this stuff. I don't think it's probably changed that much other than the electronics have probably been highlighted, updated a little bit, but the general process is what it is. It's a magnet. You're magnetizing a part. You're putting some magnetic powder on it to see if there's going to be anomalies show up. Sometimes you have a black light because it's a fluorescent. You're using fluorescent powders, but this is a general purpose stationary magnetic particle test bench. You're not using a yoke. Here's demagnetization equipment. You've got a demagnetization coil, a carriage, timer and switch, and an indicator light. But this is the equipment you would use to demagnetize a very large part. Not very large, but a large part. It is often necessary to perform the magnetic particle inspection at locations where fixed general purpose equipment is not available, or to perform an inspection on some structure without removing it from where it's at. These units can be used for, looking at things that have cracks and whatnot. Portable units supply both alternating current and direct current. This unit is only a source of magnetizing and demagnetizing current and does not provide a means for supporting the work or applying the suspension. The magnetizing current is supplied through the flexible cables. The cable terminals may be fitted with prods as shown in the illustration or with basic procedures and techniques for magnetic particle testing. Magnetic particle testing can be broken down into 5 basic steps: preparation of the test surface, magnetization, application of magnetic particles, inspection, and then demagnetization. Here we've got a picture of an individual doing a magnetic particle inspection utilizing a yoke, and you can see him spraying the powder. The powder's kind of got a red color to it so that it shows up, that it gives a good contrast. So he's going to induce a magnetic field in the part, probably going to induce it from a couple of different directions so that if there's a defect in there that is running parallel to the lines of flux on his first check, he's going to turn it 90 degrees, and then he's going to get it on, hopefully find the defect, because if it's running parallel the first time, then it will be perpendicular the second time. Here's another picture of an individual doing some magnetic particle testing. You can see he's got the yoke and he's inspecting some circumferential welds on some pipe or tubing. And you can see he's got the spray. I think it's got a spray-on type of powder, but it's got the iron in it. And hopefully he'll find, well, hopefully he doesn't find defects, but if there's defects there, hopefully he finds it. The advantages of using magnetic particle testing are: complex shapes can be tested, cracks filled with paint or other foreign material can be detected, unlike using dye penetrant. Large numbers of similar parts can be rapidly tested and automated. Small fine cracks can be detected. Subsurface discontinuities can be located. Cracks can be located through thin non-metallic coatings. Estimate of the crack depth, easily learned, and it's a relatively low-cost system or process. Disadvantages. The disadvantages of magnetic particle testing are only ferromagnetic materials can be tested. High electric current is required to magnetize something. Demagnetization required in some instances. Extreme care to avoid burn spots. And this is burn spots on the parts you're magnetizing. Difficult to detect small defects below the surface. Cleaning required after test. Complex shapes may require more than 2 magnetizations.
Summary. In this module, we touch base on magnetic induction fields, magnetic particle testing, equipment and materials, basic procedures and techniques, magnetic particle powders, magnetic particle inspection of welds, and then the advantages and disadvantages of magnetic particle inspection.